Back in Unit 2, when we were studying linear regression, we saw several examples of computer output that was standard for statistics programs used by practicing statisticians or even college-level students. And like we did in those chapters, we might also be asked to interpret computer output for confidence intervals or even hypothesis tests along the way. So this is our first example of that. This one is super simple in that all you have to do is basically write a conclusion. Conditions will already have been checked, the procedure will already have been done, everything is finished down to the conclusion, and you just have to fill in that blank. So let's just check it out. The study of 902 decisions, that's a sample size, made by the Nebraska Board of Parole. So this is the board that interviews, probably investigates prisoners to see if they're up for parole, to see if they actually do get paroled. Produce the following computer output, assuming these cases are representative of all cases, that sounds like a condition check, that may come before the board. What can you conclude? So we're just writing a conclusion. So we got to be able to read this and interpret it. So we've done a z interval for proportion, which is the same thing as a 1 proportion z interval. 95% confidence, that's our confidence level. And then we have P with no hat, that means the percentage of all prisoners who are paroled. So these are prisoners who successfully came up for parole and were able to get out. Is between this lower bound and this upper bound. We just got to put that in a sentence using our magic sentence. And I have some scribble down here where I butchered the magic sentence earlier, so I'm going to write the magic sentence over to the side because that's the only space I have left that's convenient. We are 95% confident that between 56.1% and 62.5% of all prisoners, who go before the parole board will obtain parole. That's probably fancier than I need to be. They're gonna get out of jail. Okay? Write the magic sentence, do it in context, done with that one. So that's the easy step for the day. So the rest of the lesson for day 3 is about what 95% confidence means. So this is a conclusion. This is an interpretation of a confidence interval in context. That's a natural part of a confidence interval anytime we construct one. Sometimes you're asked an additional question after you summarize that's phrased something like, what does 95% confidence mean? That's a different question, and we need to tackle that today. Now, ideally, we would have passed some bingo chips around a few times. Everybody would have taken a sample of bingo chips. We have about 240 bingo chips in this bag. So a sample size of 24 is big enough to meet the NP/NQ having to be at least 10 requirement and small enough to be no more than 10% of the population. As long as we mix them up, we get some random samples. So already have a few of them done. If we had been in the classroom, I would have passed the baggie around and everybody would have collected a sample of size 24, counted number of blue, and found a percentage of blue. So number of blue over 24, and then build a confidence interval. So, well, let's just do one of those. And we have a serious issue with, serious issue with a reflection. So I'm going to pull out a sample here of about 24. So I've stirred them up first. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I need 6 more. 19, 20, 21, 22. Need 2 more. 23, 24. Okay, so I have 24. And of those 24, 1, 2, 3, 4, 5, 6, 7 of them were yellow. That means the other 17 are blue. So I have 17 blue out of 24. And I'm going to create a confidence interval. I've already checked my conditions. I know I'm going to do a 1 proportion Z interval. And I want to construct an interval pretty quickly so I can look at a bigger picture. So I'm going to go straight to my calculator tool. Statistics is number 6 in the menu. Confidence intervals number 6, 1 proportion Z interval number 5, and I had 17 successes, that was blue, out of 24. I'm going to do a 95% confidence level and create a confidence interval. So I have a p-hat at about 71% and a lower bound at about 53% and an upper bound at about 89%. Okay, so I'm going to scoot these out of the way for now. We'll round those up later, and I'm going to draw on this paper my confidence interval. So notice there's already some here because I did some ahead of time so that we'd have some to look at. So if we were doing this in class and everybody took their own sample, each person will have their own personal confidence interval to put on the board. The one that I just took had a middle at about 71%, so I'm going to follow over here 71%, and that's about here. And the lower bound's about 53%, so about here, and I'm getting far enough away it's hard to really line that up well. 89% is up here. Now, this should be a symmetric interval, so the p-hat, the point estimator, is in the middle, and the distance from there to each edge is the margin, and those margins should be equal, but I'm an imperfect artist, so those are going to just have to do. So this is one of several confidence intervals that was built from taking samples from the plastic bag. So somebody took a sample, found a p-hat of somewhere around 63% and the interval, and someone else found one a little bit smaller, 55-ish%, and made an interval. Somebody else found one about 70-something%, made an interval. This one was lower than the rest. There's a couple up here that's kind of higher. So what would have been really nice is if we could all together have built a set of confidence intervals to look at, all from the same bag. So these are a bunch of possible samples that can be collected from the bag. There are infinitely many samples that we could collect, and there are infinitely many confidence intervals that we can draw. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's about half a class worth. So not as many as I would normally like to see. But since I'm limited on time, 13 will have to do this time. So when I look at these, there's a couple patterns I want to see. One, the closer the p-hat is to the middle of this whole, if I kind of, I don't know, maybe kind of make an oval out of here and draw a line kind of through the middle of it. The ones that are closer to the center are bigger intervals. And this one up here closer to the top, this one had a fairly high p-hat of around 90%. It's actually a little more than 90. It's a smaller interval. This one had a p-hat in the 80s. It's a smaller interval. But when we have p-hats in around 50%, like this one, that's the longest one that we see. So the closer our p-hat is to 50%, when p-hat's 50% and q-hat is 50%, turns out that's your biggest possible confidence interval for any data set, for any population from which you're pulling a sample. So if you're trying to really get the biggest margin you possibly can, then you're going to be looking at something where p-hat is somewhere in the neighborhood of 50%. So the ones in around 50% p-hats are going to be longer. Higher ones up are going to be shorter. If we had any that were kind of down here, they would have been shorter as well. This one actually stretches up to 102%, which isn't really technically possible because you can only pull 100% blue out of the bag. You get 24 out of 24. So this one gets into sort of impossible space. And the reason it does, the reason we have one of those that stretches that far is because we just barely met the success failure condition for this particular sampling distribution. Just 24 was just barely a big enough sample size to squeeze in the NP NQ at being around 10. And because it was so close to just barely being 10, you can get these very unusually high or very unusually low samples that may not make the most sense in the universe. But they're still possible because sampling variability says you can get anything that could possibly be pulled out of the bag. So the next sort of enlightening piece is I'm going to tell you what's in the bag. This bag has 62% blue. So I'm going to find 62% on this graph. It's about here. I might be able to tell better here. 62.5% is about there. Now remember, the goal of taking a sample and constructing a confidence interval is to make a prediction about the population and have a pretty good level of confidence about your prediction. So if I look at all these confidence intervals, this first one, it captured the true proportion, and the p-hat was pretty close to this. Actually, that may be a little bit low. 62 is probably a little higher than that. So the p-hat was pretty close to the truth. The second one was a little bit lower. This one was a bit higher. But if I look at the entire interval, this interval, this interval, this interval, this interval, this one, these first 6 intervals, they all contain this 62%. They contain that true P in the population. Or sometimes we say they capture the true proportion. This one right here was too high. It missed it. This one here was a little bit too low. It missed it. So this one was an unusually small number of blue. This one was an unusually large number of blue in the sample. And this one was a super unusually high one. That was a real anomaly, but it does happen because sampling variability has variation. But most of our confidence intervals captured the true proportion. Now, if we did this more, what we would find is the majority of our confidence intervals would capture the true proportion at 62%, and just a few would miss it. So here's the great question of the day. What percent of confidence intervals, if we could do this over and over again forever and make all the possible confidence intervals in the whole universe, what percentage of the confidence intervals would actually capture this true proportion right here? And hopefully you said, 95%. Yeah. What should happen in a perfect world if we did perfect sampling and randomized over the long haul? For every 100 samples that we take, 95% or 95 of those samples should have confidence intervals that capture that true proportion. The other 5% are going to miss it. So if we take 100 different samples, 95 of them should be good ones that capture the truth, and the other 5% are going to either be a little too high or a little too low or a lot too high, possibly. So 95% confidence means that 95% of all samples are going to have confidence intervals that capture the true proportion of the population. Okay, the rest of the notes are just putting that on paper, that big idea. So let's go back to the notes and let's summarize this. This is going to be over with pretty quickly. So, big picture, what does 95% confidence mean? Suppose I have yet another tub of brown beans and white beans to pass around. You remember the tubs of beans. We'll just pretend to pass them this time because it's kind of hard to do that from afar, from video. Each of you takes a sample, calculates a confidence interval for your sample. So let's say that we have 0% here, 100% here, and somewhere in between we have the actual percentage of white beans. And I'm thinking we had a tub with something like 10% white beans. And so the true P was here for the whole population of beans in the bucket. If we create a bunch of confidence intervals, and I'm going to make this go a little bit faster, so I'm not going to be so fancy. If I have an interval that lies here, an interval that lies here, an interval that lies here, interval that lies here, interval that lies here, one here, I'm just making these up. This is just a real rough picture of confidence intervals. If I made 100 of these, 95 of them should go through that P, and the other 5% of them should not capture the true P. So 95% capture P, and the other 5% miss it. Miss the P. They're too high or too low. So, to summarize that, a few samples will have a p-hat that's unusually lower or higher than the true proportion of white beans in the tub, but most p-hats will be within 2 standard deviations of the mean, about 95% of them. So if we collect all possible samples, which we have yet to do, because we don't have enough time, we won't live long enough, of beans, 95% of them should have confidence intervals that capture the true proportion P of white beans in the tub, or in our case, of blue bingo chips in the Ziploc bag. So, here's the pretty picture from the textbook. When you are asked on the AAP exam, what does 95% confidence mean, or 90% confident, or 98% confident? It's the same question, you just change your number. That percentage of all the confidence intervals from all the possible random samples will contain the true proportion P. So here's a better picture. You have one right there that misses it, one right there that misses it, one right there that misses it, but the majority of the confidence intervals capture the true proportion. Now, when you interpret this, when you explain what 95% confidence means, you need to throw some context in. 95% of all possible samples of bingo chips will contain the true proportion of blue bingo chips. Except that you have to say 95% of all the confidence intervals from all the possible samples. And that's where you can get into trouble if you're not really careful. It's about what the confidence intervals do. So you have to start there. Whatever your percentage is, that percentage of confidence intervals that are made from all the possible samples of bingo chips will capture the true proportion of blue bingo chips in the population. This is a sentence you need to practice. So we have some homework to help you do that. Day 3 homework's on page 490. That is in your notes packet, and that's your next assignment.